Check it out now, y'all.
nanoHUB-U online instruction.
Welcome to week 2. This is Edwin Garcia. This is lecture 2.1. I'm going to talk about the equilibrium aspects of what specifies the voltage and charge in a rechargeable battery. In order to start a discussion, I want to start by presenting concept of thermodynamics for electrochemical systems. Okay. First of all, let's think of two phases, an electrically active phase, okay, and some reference against which that phase, beta or alpha, is at equilibrium, okay. In order for this material to equilibrium, they have to exchange energy between them, okay, and the first type of energy that you can exchange between two phases is not necessarily the chemical or the electrical. The first one corresponds to the thermal energy. In order to describe it, we need to specify two thermodynamic variables: temperature, right? That is, the amount of hotness that the material has, okay, and the entropy. The entropy is a quantity that has to do with the amount of heat exchanged by that phase with its surroundings, and it has to do with at the most fundamental level is thought to be related to the amount of disorder that the individual atoms or molecules may have in the system, and they come in pairs. So if you consider the pair temperature entropy, the pair has units of energy. Okay. Now the next pair of how the energy is exchanged between these two corresponds to the chemical variables. In this case, mu sub I corresponds to the chemical potential of the ith component. Okay. That is how much energy per unit mass, okay, is necessary to put into that system, and so that system can store it. You can think of it of all the local interatomic contributions that develop during the assembly of this material, how statistically they combine both van der Waals, all of them van der Waals, Coulombic, ionic, energetics to build this solid. And, well, that is correlated to how much mass you have associated with that. That corresponds to n sub I. Okay. Again, the same way that the TS pair has units of energy, the mu I n sub I pair has units of energy. How many components we have, that depends on how many species you're considering. In this case, we're going to be considering two. Say we talk about the lithium ions and the electrons as the two species that the system is handling, just for the purposes of the discussion. Now, this wouldn't be a battery. We don't include the electrical variables, which obviously are going to be the voltage and the charge. Okay, the voltage can be thought of the amount of charge necessary to be brought from some reference, say from infinity, to build the solid or the liquid. Okay, and Q corresponds to the total amount of charge that is actually being stored in the system. Okay, so again, phi corresponds to the energy per unit charge, and Q corresponds to the total charge, so the product gives you units of energy. And each of them, you can see, have units of energy. You can think of other energetic contributions that I'm not putting here. For example, you can think of the PV term, P being pressure and V being volume. So pressure has units of joules per unit volume, and V obviously has units of volume. So the product gives you the amount of mechanical energy that you store when you compress this mechanically, which I'm not including here, but you can see an equivalent derivation or an equivalent formalism based on adding those additional variables. You can think of other contributions like surface tension that may very easily fit here in the system. Now, those energetics, the most fundamental statement of energy based on these variables corresponds to the combined statement of the first and second law. Okay, and that is given by this equation. In this case, U corresponds to the internal energy of the system. And you can see that what we're saying here is that the internal energy stored in, say, phase alpha corresponds to the amount of heat exchanged with the surroundings, with how much amount of component 1 and component 2, and how that accounts for the chemical contributions and the electrical energy stored in that system. Okay? Ideally, in a battery, what we would want is to convert all the energy, all the chemical energy, into electrical energy and back. Okay, that will give us a battery with 100% efficiency. Unfortunately, we will always have this TDS term, this entropic term, which really corresponds to the second law of thermodynamics, and tells us that for this electrochemical engine, there will always be some efficiency some laws that will limit our efficiency to be always less than 100%. Okay, so in principle, we will never be able to reach 100% efficiency on any battery in the universe. Now, that said, I'm just not going to identify the terms. There's a heat term, as you can see there, okay, a chemical work term, and some electrical work contribution. Okay. Overall, again, each of these contribute to the actual thermodynamic state of each of the phases, and what we want to do is define a system where phase alpha and phase beta exchange energy with the surroundings, so that we can find the state where this system, when they're both in contact with each other, they're equilibrium. So what we're going to do is we're going to put some imaginary walls across this boundary of the alpha and beta system, where there's no heat being exchanged with the surroundings. There is no mass that can escape or come out. There's also no charge that can escape or enter the system. So if there is a gain of energy from phase alpha, will be as a result of that energy that beta passes to alpha and the other way around. Okay, so we're talking about that any infinitesimal change of energy that the material will gain will be a result of the infinitesimal changes of each of the individual contributions, and how those individual changes are changes of energy are a result of the exchange between phase alpha and phase beta. Okay, so this statement is universal and applies for every single type of chemistry. Specifically, we can say that this applies for phase alpha, right? So I can rewrite the same expression for alpha, that now I could just put alpha embedded in beta, and beta, it's isolated, so it can only exchange energy with alpha. So you can say that the internal energy of alpha corresponds to the heat exchange with, in this case, with beta. The change of energy is a result of gain of component 1 or 2 with the surroundings, and the voltage or charge contribution gain that it may have gained from beta itself. Okay, and what applies for alpha also applies to beta. So you can see a very similar statement where, to distinguish between both phases, I have relabeled this super indices to be beta, and physically what we want, okay, is to assert the fact that the system is closed, meaning that if I gain some energy in U, okay, in the beta system, then the system alpha is giving it to it, so that you can think of a system where the energy is conserved. So the amount of energy for alpha and the amount of energy for beta, the sum of both contributions add up to a constant. Similarly, if this system occurs at equilibrium, the amount of entropy that I have for alpha and the amount of entropy that I have for beta shouldn't increase or decrease, for that matter. The contributions for both alpha and beta should be constant, because that's another constraint. We should also impose a constraint in mass. Obviously, the amount of ions of component 1 should remain the same. We shouldn't be able to destroy or create any mass. So N1 alpha plus N1 beta should also be a constant, just like N2 alpha plus N2 beta should be a constant. We do not want to create any new atoms or to inject any atoms into the system. And the same, the charge. The charge cannot be created or destroyed, can only be transformed to something else. So that's accounted for that other contribution. And mathematically, is written in terms of these 4 equations, which basically tell me that the total amount of energy corresponds to the sum of the energy of alpha plus beta. The same with the entropy. The total entropy is the sum of the entropy of alpha plus the entropy of beta. And the amount of mass for component 1 is the contribution from alpha and beta, and the contributions for mass for component 2 corresponds to the contributions from alpha and beta. Okay, now the charge happens to be related to the concentration of each species, because component N1 has a valence Z1 and component N2 has a valence Z2. So each of those valence that each of them may have, in this case of opposite sign, will add up to specify how much charge is stored in alpha or beta. And that's written in these terms, right, where we can say that the amount of charge in alpha corresponds to the basically weighted sum of the contributions from the amount of mass for each contribution. In this case, n goes to 2, but you can see this for a multi-component system going to 3 or 4 or 5, where F is the Faraday constant and Z sub I corresponds to the valence of the ith species. This occurs for alpha, so you can say the exact same thing for beta, and basically these specify the constraints of the system. Okay, fundamentally this description is known in thermodynamics as the fundamental problem of thermodynamics. Okay, and now that we have these conditions, we can specify now the equilibrium of the system. Okay, now we're back to our cartoon. Now, if the system is truly at equilibrium, the total amount of energy in the system, and even if it's out of equilibrium, the total amount of energy is conserved. Okay, so we can enforce that by saying that if we apply that to the condition that you saw on the previous slide, that the differential amounts of energy of alpha plus the differential changes of energy of beta, they should basically cancel each other. So if for any reason the energy of alpha fluctuates, the energy of beta should fluctuate with the opposite sign, so that the sum of both should always give us an exact 0. Okay? Now what we can do here is we can substitute the statement of the first and second law here and here. Okay? And that will give us a much more allows us to substitute what's occurring on each individual phase. Now, we need to include what occurs on the other relationships. We can say the same thing, because now we know that if these fluctuations occur, there may be a result of the internal fluctuation. So if there's a fluctuation in the entropy at equilibrium, that should be balanced by fluctuations of entropy in beta. The same applies for fluctuations in composition. So fluctuations of composition in component 1, basically if I take from component 1 of the alpha phase, from alpha, I take it out and put it in beta, that should account for energy conservation by having that change of component 1 should be minus negative the component 1 of the other phase, and the same with component 2. Okay, now if we do that, we can also say the same thing about the amount of charge. Okay, so if I take charge out of alpha and put it into beta, as would occur in a battery, then that charge cannot be created or destroyed. Basically, it's just moved from one system to the other one. And now and if we substitute these relationships into this relationship, into du alpha plus du beta equals 0, using the first and second law, you will find this expression. This expression allows you to specify to be closer to the conditions of equilibrium that we're looking for, except that we still have lose the amount of q beta and how it relates to n1 and n2. So in order to do that, we need to take the differential expression of how charge relates to the amount of each component. Okay, you can take this expression and substitute it in here, and if you rearrange terms, you will find this relationship. Okay, basically this is telling you the total amount of energy in the system is, the changes in energy are 0, the total energy is conserved, but that does not preclude from any local fluctuations in entropy or fluctuations in mass from component 1 or component 2 occurring in the system. Okay, but regardless of what fluctuations may the system have, which should be balanced by the other phase, the total energy is conserved. And the only way where that will happen, that is where ds beta, dn1 beta, and dn2 beta are non-zero, it is if the prefactors that multiply each of those differential contributions are 0 at all times. Okay? So what we're saying here is that any fluctuation associated to these differential changes should not alter equilibrium. Okay? The fluctuations should not impact the fact that the energy is conserved. So what does that mean? That using the only thing that is possible is that T beta equals to T alpha, which is actually something that we know, because we know that at equilibrium the temperature of the alpha phase has to be perfectly balanced by the temperature of the beta phase. Okay, and well, we can write this mathematically in this way. Basically, T alpha equals to T beta, but well, we already knew this one. Okay. We also know that based on what we derived on the previous slide, that the chemical potential of the component 1 of the alpha phase modulated by the voltage with respect to some reference that the alpha phase may have is going to be equal to the chemical potential of the beta phase plus some shift associated to the voltage with respect to some reference that the beta phase will have. And the same applies for component 2. The exact same thing. If the systems were if this system was electrically neutral, then in other words, if there was no charge contribution, the voltage could be ignored, and we could say that at equilibrium the chemical potential is the same, which is something we expect from a chemical system. But for an electrochemical system, we're not saying that the chemical potentials are the same. What we're saying is that equilibrium will be obtained when the sum of the chemical potential from plus some vertical shift balances out the chemical potential of the other phase through another voltage shift. Okay, and that shift, this quantity mu1 plus zf times phi, is what people define as other quantity. In this case, I'm going to use the symbol eta. We're saying eta 1 alpha equals eta 1 or beta, or the same for component 2. Okay, and people define this number as the electrochemical potential. What we're saying is that when a system is at equilibrium, the electrochemical potential, this quantity that we have specified, okay, is uniform across the system. What that means is that there could be a chemical potential difference between two phases, but that can be balanced out by imposing, or the system developing, a voltage difference, in this case of the right sign, so that this relationship is satisfied. That means that the system will develop when you have a chemical potential difference between them, in order to reach equilibrium, a voltage difference, and that voltage difference constitutes the voltage between the two phases. Okay? Another way to look at the same thing could be written like this. Okay? And basically what I'm saying here with this relationship is the voltage the voltage for component 1 for transforming from alpha to beta corresponds to the chemical potential difference between both of them divided by Z1F, okay? And specifying without the material potential with respect to alpha, or if you include the valence of component 2, the chemical potential difference divided by ZF gives you the potential of component 2. Okay. Now, this chemical potential difference divided by CF could also be thought as a Gibbs free energy transformation, which is what we saw last week, and that defines the potential the system have. What we haven't specified yet is how do we calculate that chemical potential, and in the next class I will talk about how we specify that chemical potential difference using what we know already from thermodynamics of solution for chemical potential 1 and chemical potential 2. Okay, thank you.